We're now going to look at three properties of functions, namely one-to-one, onto, and bijection. You have probably already seen these notions. We're just going to do these using sets. So let's start with one-to-one. A function is called one-to-one. Essentially, the way you remember this is different inputs go to different outputs. If I were to draw it pictorially, this is how I'll do it. It doesn't happen that two different inputs go to the same output. And finally, more precisely in the set notation, this is described as follows. That if x1 is not equal to x2, then f of x1 is also not equal to f of x2, where x1, x2 are elements of x. When you are trying to prove something is one-to-one, turns out it's kind of nicer to prove the contrapositive. So I'll just describe the contrapositive here itself. Remember that for a contrapositive, you have to flip the hypothesis and the assumption, hypothesis and the conclusion, and negate them. So the contrapositive is, so f is one-to-one if f of x1 equal to f of x2 implies x1 is equal to x2. Okay, so that's one-to-one, and I'll do examples in a minute. The second important definition we need is called onto. Onto, the slogan you need to remember is that the range is the whole target. And pictorially, this is a little harder to describe, but essentially what this is saying is that everything in the target is in the range. And if you want to describe it using more formal mathematical notation, you'll write as follows. You can make this a little more succinct using formal logic notation. So that will become okay, so for every y in y, there is at least one x that hits that path. It's totally possible that more than one inputs go to y, and that's okay. That's allowed for onto. And the final definition is a bijection. A bijection is easy. A bijection is simply one-to-one and onto. Okay, now let's do examples. I'll take a simple function from calculus. Show that the function 2x plus 1 from R to R is one-to-one. Usually proving something is one-to-one or onto, the proof is pretty straightforward. It's mostly direct proof. And for one-to-one, you might try doing a proof by contrapositive. I probably don't even need to do a scratch work here, as you'll see. If things don't work out, then I'll go back and do some scratch work. So I want to show that if f of x is equal to f of y, then x is equal to y. So let's start. Then expanding out the definition of f, we get, then I cancel out the 1. Then I cancel out the 2. I divide both sides by 2. And I get x is equal to y. And this is exactly the statement that we wanted to show. And so, and that's the end of the proof. So that's how we prove something is one-to-one. Now to show something is onto, it's here's the example. The same example is also onto. Now this one needs a little scratch work, because onto what are we trying to show? We are trying to show that for every y there exists an x such that f of x equal to y. So we're trying to show to prove a for all statement, I have to take an arbitrary y. So I pick an arbitrary y and I need to come up with an x. There's no other way to do it, such that 2x plus 1 is y. And I need to go from an arbitrary y to some x that satisfies that property. And I can work backward. So I can do 2x is equal to y minus 1. I can move a little more backward and I get x is equal to y minus 1 over 2. And that's it. I have found the x that works. And now I can start the proof. The proof is usually a direct proof for onto functions. So at first I explain what I want to show, then I start the proof. So the proof is actually starting on this line. We'll start with let y be a real number. And now I'll just pick my x. Then and so I've shown that f of x equals to y. This is exactly what we needed to prove. And that completes the proving onto is just giving a direct proof. Just give an x that hits the given y. And you need to do a little bit of scratch work to figure out which x works. And finally, if I wanted to show that the above function is bijection, then bijection is onto one-to-one and onto. So it's just proving an and statement. So I prove one-to-one and I prove onto separately. Proving these two things, and you prove this by hand, like you give separate proofs. Essentially, you combine the two proofs that we have above and form one big proof that will prove that f is a bijection. All right, so now let me give non-examples and say more things about one-to-one and onto. One-to-one depends heavily on what the domain is. And what do I mean by that? Let's consider f from R to R, where f of x is x squared. Now this function is not one-to-one. To prove something is not one-to-one, I just have to give a counter example. There are infinitely many counter examples. Let me pick one. Let's say I'll just pick minus 10 is not equal to 10, but minus 10 square, which is 100, is 10 square. And so two different things are going to do the same thing. And so it's not one-to-one. But I can change this and make it one-to-one by the following modification. And this will become an example. F goes from R plus to R. And the function is the same, but all I've done is I've changed the domain to positive real numbers. And as soon as I do that, this function becomes one-to-one, because now I'm only looking at positive numbers. And if two positive numbers have the same square, then they must have been the same to begin with. I could have also changed the domain to non-negative numbers, and that would also have been one-to-one. If I change it a little more, I can turn it into a non-example by say something like this. And now this function is not one-to-one because I have negative numbers, and minus half square is the same as plus half square. Okay, so being one-to-one very seriously depends on what the domain is. What about onto? Onto is flipped. Being onto very seriously depends on what the target is. So I can take the same example. Sorry, I forgot to do it. Sorry, I am doing examples here of one-to-one and here of onto. Okay, so now I can take the same example, and this time it's not one-to-one, it's not onto. So what do I want? I want a value of y which is not hit by f. So I want a number which is not a square, and for any negative number works. So I can take y equals -1 is a counterexample. There is no x. Okay, so that's a counterexample for onto. Now, if I want to make this function into an onto function, this time I'll have to change the target instead of the domain. So this will become f from R to non-negative reals. I'm not changing the function itself, I'm just changing the target. And now this is a valid example, because for every non-negative real, there exists a real number which hits it, which is the square root. Here I can't make the target positive reals because I would have no place to send 0 to. And finally, for bijection, bijection depends on both the source and the target. So if I wanted to make x square a bijective function, then I'll have to change both the domain and the target. And now this function is both one-to-one and onto, and hence it is a bijection. Okay, so that's these are non-examples and some properties and subtle points about one-to-one and onto functions.